So now let's continue with 17.3. So conservative vector field. So basically, if you recall, a conservative vector field is a very nice object in the sense that you have a vector field and this potential function. Okay, so you essentially have a scalar function that gives you the gradient that agrees with the vector field. Okay, and then the potential function is in a sense an antiderivative for your multivariate for the vector field. That's a multivariate function. Okay, so in this sense, this kind of antiderivative can help you integrate. Okay, and this so in this section we are talking about the fundamental theorem. Fundamental theorem of line equals. So if you recall, for a function that you're integrating, and you know what the antiderivative is for that integrand. There's a theorem called the fundamental theorem of calculus, right? But here we essentially extend that fundamental theorem of calculus along for a line integral. Okay. Recall fundamental theorem of calculus. Fundamental theorem of calculus. So basically, when we have the definite integral along the interval from A to B, and let's suppose we know the integrand is cap f prime, which is just saying, okay, we are integrating a function, but we know the antiderivative. Okay, the antiderivative is just cap f. In that case, we just evaluate the antiderivative at the endpoint minus the antiderivative evaluated at the start point, okay, of the interval, right? So this is the fundamental theorem of calculus. So here, this function that we're integrating, as long as you know the antiderivative, then you can just translate the problem into the evaluation of the antiderivative at the endpoints, right? But now here for a conservative vector field, we what do we know? We know, in a sense, the potential function is the antiderivative there, right? So let's state the fundamental theorem of line integrals as a theorem. So here we have a line, we have a curve, right? So let curve C be a smooth curve given by the vector function of t is having a standard parameterization where my t parameter goes from A to B. Let f be a differentiable function such that the gradient of little f is continuous on cap C. Then, so essentially, this gradient nabla f is actually that vector field of this potential function little f. Okay, and then the line integral along the curve of the vector field nabla f starting with dr. Okay, so this is the form that you see for the left hand side of the fundamental theorem of calculus, right? So you're integrating a function, and you know what the potential function is for here. Okay, so this if you write down the statement for the right-hand side, this is exactly the evaluation of the function along the curve at the endpoint minus the evaluation of the function at the initial point. So this is, you can see this highly relates to the fundamental theorem of calculus. Okay. And then here we're going to prove it. Prove. So you basically see on the right-hand side, we have f evaluated at the vector function r in place of that cap f, right? So we use another name to that function. So we let phi of t be a function defined as the evaluation of the little f along the curve. Okay. So phi of t equals to f of x of t, y of t, z of t, which is, of course, if you write it another way, this is just f evaluated along the vector function. Okay. Then, so if we do this derivative with respect to t, that's chain rule, right? So the function little f evaluated along the curve. So this is a univariate function. Okay, so we have only one parameter t there. By chain rule, so basically f, if you draw the diagram, tree diagram, so f relies on x, y, and z. Right? And now x, y, z, they all relied on the parameter t there. Okay. So if you do the derivative, the derivative of phi with respect to t, that's phi prime, that equals to del f del x times dx dt plus del f del y dy dt plus del f del z, finally multiplying by dt. Okay. And here, what do we see? Actually, we see this is the dot product between the gradient and your tangent direction, right? Basically, the situation here is that if we have a conservative vector field, then this integral of the vector field starting with the tangent direction, this integration will be essentially easy to calculate because you will have a potential function there, okay? And the result of the integral is exactly the potential function evaluated at the endpoint of the curve minus the evaluation of the potential function at the beginning point of the curve, okay? Initial point of the curve. So, and we can see that the proof is straightforward because if you define this composition function, okay, so basically this is just the f of r, okay, f of vector function r. This is just the evaluation of your potential function along the curve, right? So that's a univariate function. We are now calling it the phi, okay, and then. So basically, this once again, this function is a univariate function, and like right here, okay. So this function is actually that's anti-derivative that you can think about in the fundamental theorem of calculus. So of course you want to think about doing the derivative of that, and the derivative tells you, okay, this follows the chain rule, and we see the derivative is exactly this expression. Okay. So. Now we integrate. Thus, so basically, if we do the integral along the curve of this vector field starting with dr, you know by definition the calculation is going to be the definite integral from the starting point A to the endpoint B of the parameter, and we do the evaluation of the vector field, starting with r prime, the tangent direction dt, right? And what do we know? We know now this dot right here is exactly that function phi, taking the derivative, okay, from the previous line, right? And now, so here we can do the fundamental theorem of calculus, right? So this is a function phi prime that we're integrating. We know the antiderivative is phi itself. So, right, fundamental theorem of calculus, this equals to our antiderivative, which is phi, evaluated at the endpoint minus the phi, and the antiderivative function evaluated at the initial point. Okay? And then we translate back to f of rt, and so this is the evaluation at the endpoint minus the evaluation at the initial point. Okay. By the way, we define b, and we're done. Okay. So you can see that as long as your vector field is conservative, okay, then you can find such a potential function, and then the integral becomes easy. So you just evaluate that potential function at the endpoints of the curve that we done. Okay. So a quick remark that relates to this conservative vector field is that, okay, now if your curve is closed, meaning that the start point and the end point are the identical points, okay, if these are the same point, then what do you know? You know that the difference is 0, right? So remark, if C is a closed curve, meaning that it is described by the vector function of t, the parameter goes from a to b. But here we have the start point, well, with the initial and the end are the same. Okay. So that means basically you have a curve, but then you just ends at where you start with. Okay. So it's to illustrate, you possibly have a curve like this, but you end at exactly where you start. Okay, I'm going to put the point more solid so that it looks smoother. But this is saying my R of A equals to R of B at the solid point right there. Okay, so the orientation is just counterclockwise in the figure, but this is the curve that we have. Okay? So basically, it just tells you, okay, at the black point, t equals to A, it will start, and counterclockwise, going down and then going up, back to the black point where RB is at the same point. So this is a closed curve, okay? So it starts where it ends, and then for the evaluation here, it will give you f of RB, which equals to f of RA. So this difference, no matter what the evaluation value is, the difference is going to be 0, okay? So if this is a closed curve, and actually, all of a sudden it comes, and if the vector field kappa is a conservative vector field, that means there is a potential function little f such that kappa f is the gradient of the little f. Then from the theorem that we have for the line integrals, so the line integral of the vector field along the tangent direction of the curve equals to. So now we know that nabla f is the gradient of little f, and here we're integrating that along the curve. Okay? So by the fundamental theorem of the line integrals, this equals to the measure function evaluated at the endpoint minus the evaluation at the initial point. And we know that these are the same points. So this equals to 0. Okay. This tells you, okay, if you have, as long as you have a closed curve, cap C, and if you have a conservative vector field cap F, then this line is always a 0. So, in another way that you can think about it is that, so these 2 points, so these two points, so if you only think about these RB and RA, and you just consider this as a point A and a point B, okay? So if you pick a start point and an end point and you draw 2 curves, right? So that will form you 2 different passes, and these 2 passes will give you a closed curve. Okay? So this is what they call path independent. So let's write down that remark. If the vector field equals to nabla F is a conservative vector field, and we now have 2 curves, okay? C1 and C2 are 2 smooth curves with the same terminal points. So meaning that they have the same initial point and they have the same destination, okay? So let's say that's cap A, and let's say that's destination is cap B. So what you know is, as long as your curve is smooth, like this, then the line integral only relies on the pleasure function evaluated at B minus the pleasure function evaluated at A, right? So that's C1. But now we're just saying, okay, now if we have a C2, excuse me, that's also starting from A and ending at B, as long as it's smooth. Then by the same theorem, so this line integral along C2 of the vector field starting with the tangent of the curve also gives you the same value. Okay? Consider the closed curve C that consists of C1 and negative C2. We have a combined closed curve C. So basically, what does it mean? So basically, here C1 is pointing from A to B like that, right? But then if you negate C2, that just say, okay, I'm starting now from B back to A, and that's a closed curve that we unify to be this new curve, closed curve C. Okay, so we know now the line integral integrated along the entire closed curve C is a 0. So, and we also know that this line integral along the entire curve C can be separated into 2 pieces that are smooth. So this thing equals to the line integral along C1 plus line integral along the bottom part, which is the negated C2. Okay. And then further equals to the line integral on C1 minus the line integral on C2. Okay. Because whenever you negate that curve, you are simply negating the line integral of that original curve. Okay, but that tells you what tells you. So no matter C1, regardless of C1 and C2, as long as they have the same pair of start and destination, then the line integral will be the same. Thus, the line integral along C1 equals to line integral along C2. And this is called independence of path. Thus, we say the line integral. So now, so this C is a general C. Okay, so this is the general curve. So line integral is independent of path. Because of the conservative vector. Okay. So now you see that the conservative vector field is conservativeness. It's actually a conservativity. So basically, that this property is very important, and it gives you both that the integral is always a zero for the closed curve, and also the same thing that it is independent of path. Okay, regardless of the path that you choose, as long as they have this the fixed start point and another fixed the destination, then the integral doesn't change. Remark? Conservative vector fields are also called path independent vector fields. This is due to the following theorem. So basically, there's a slight difference here about the terminology. So we from the above this discussion, we know, okay, if you have a conservative vector field, then this is path independent, right? But then, in a sense, this statement can be reversed. Okay? So if the vector field is path independent, it's possible that it's not conservative, but we have some special conditions to ensure this direction of argument. So that's the theorem right here. So the line integral is independent of path if and only if this line integral always give you a zero for every closed curve cap C in the domain of the vector field. So this first sentence of the theorem just summarizes what we have discussed. basically it's path independent if and only if for every closed curve the integral is 0, right? So here this if and only if this says okay, the former statement and the latter statement they are equivalent. Okay. But now, moreover, assuming open and connected domain. The above is true if and only if capital F is a conservative vector space. So here we are giving the condition that the path independence implies conservativity of the vector. So basically here the condition is this one, okay, right here. So as long as the vector field is having an open and connected domain. So to give a concrete example that it's not open and not connected, it could be something like this. So the vector field is defined on two separate subsets of the two-dimensional plane. If this is the case, then even though the vector field may be path independent, but it will not be conservative over the entire domain. Okay, so you cannot do this conclusion when the domain here is not connected or not open. But this is just a side comment. That being said, if the domain of the entire vector field is let's say R3 or R2, then you can say the path this independent of paths and the conservative vector field, they are the equivalent property. Okay. So for more details, see theorem 17.5 and section 17.3 on the textbook. Okay. So here, the takeaway from this section is mainly that if you have a conservative vector field, then so the line integral will be path independent. And if you are integrating on a closed curve, it's always giving you a 0, right? Remark, the final remark. So here, this is about notation. Okay? If cap C is a closed curve, we will use notation. So this is the notation. Basically, we have usually we have the integral line integral along the curve C of f starting with dr, right? But here, to indicate that this is a closed curve, what we're going to do is we draw a circle at this integral symbol to indicate that this curve is closed. Okay. So this is some kind of a notation that you probably have seen somewhere else, but it means the object that this curve C that you're integrating is closed. Okay, so that's the last comment. All right, so this is the line integral. So you see in this section we have seen the definition of the line integral. We started with this line integral. So we started with the line integral like this form, right? So this is a vector field starting with the tangent direction of the curve. And then we later realized that, okay, So f starting with dr, this is essentially just integrating a scalar function that is with respect to the plan, right? So that's another definition of the line integral that we established. And finally, we realize, okay, if we're just integrating one along the entire curve, that's actually doing what? That's actually just calculating the plans of the curve that we have, right? So we have established actually three different line integrals